As we get set to start chapter 5, we're looking at probability distributions. And so probability distributions, key concepts we're looking at here. Remember, we're talking about a random variable. Each experiment that we're conducting is asking a question, and the random variable is the answer to that question. For probability distributions, we're looking at numerical random variables, or what we'd call quantitative random variables. We'll look at a probability histogram, which is just a graph of the probability distribution, and we'll talk about some calculations, the mean or expected value, standard deviation, and variance of those probability distributions. And then we'll talk about how this applies to hypothesis testing and statistical analysis. Probabilities that are significantly really low, things that are very unlikely to happen. What does that mean? Or things that are significantly high, things that are very, very likely to happen but don't. And what does that mean? So a random variable, again, is the result of a single numerical value and is determined by chance. So a lot of books define something called a chance experiment or a random experiment. And the random variable is the result of that experiment. We have no way of predicting what that variable, what that result will be, but we can determine how likely it is to have certain results. And the probability distribution is just a table or other display showing all those results and then the probability of each of those results occurring. Typically, it's shown in a table. That's what most of what we do will be is a table. It's easier to calculate off of it. Sometimes it is displayed as a graph. So given each of those random variables, we will be looking at those probabilities. So an example of a probability distribution would be this one here. This is if you're surveying students and asking how many hours a night they spend on homework, and then the probability of them spending that many hours. So this is the hours spent on homework in this column. Then this is the probability of responding with that many hours based on experience. So a discrete random variable, we're going to be starting with discrete probability distributions. Next section goes into continuous probability distributions. So with a discrete random variable, we can, in most cases, list out all the possible values and then their probabilities. Next section with the continuous random variables, we have to rely on the graphs. An example here might be rolling a die. What's the probability of rolling a 2 or whatever? We can list out all those possible results, 1, 2, 3, 4, 5, 6, and the probability of each. So the continuous random variable, as I mentioned, has an infinite number of possible results. So we can't list them all out. Another consequence of this is the probability of getting a single value has to be 0 because there's an infinite number of possible values. If any of them had a probability bigger than 0, they would add up to be something larger than 1. And that is one of our qualities of our probability distributions that we have to stick to. And so here that brings us up. So the requirements of our probability distribution that we have to make sure we meet. First of all, we're looking at numerical random variables, not categorical. Second, the sum of the probabilities has to be 1. They have to add up to 1 because 1 represents 100%, which would be the whole thing. Now in practice, because we sometimes have to round those probabilities to express them, they might round up to 0.999 or 1.001 or something close to 1, and that's okay. We know that that's just rounding errors that are causing that issue. Also in our probability distribution, each individual probability, remember P of X represents the probability of a certain event occurring. Each of those individual probabilities has to be between 0 and 1. If the probability is 0, that means it's impossible. So we can't have a probability less than impossible. And if the probability is 1, that means it is guaranteed. It's definitely going to happen. We can't have a probability better than definite. So here we're going to look at an example of births. So giving birth to 2 children, and our variable is going to be the number of female children out of those 2 births. So we look down here, assuming that they're equally likely, as we did with our classical probabilities. Probability that none of those 2 births are going to be female is 0.25. Probability that 1 out of those 2 children is going to be female is 0.50. And the probability that both will be female is also 0.25. This is a table representing that probability distribution, where this first number over here represents the value of the random variable, 0, 1, or 2, and this column here is representing the probability of that value occurring for the random variable. So with 2 births, the number of females can be 0, 1, or 2. That's where we got those values. And then the the numerical random variable is representing that number of female births. The total probability, we added it up, 0.25 plus 0.5 plus 0.25 gave us 1. So that's saying this column adds up to 1. And each of those probabilities is between 0 and 1. So we verified that that is a legitimate probability distribution. So we know that it satisfies all of the requirements. We could express it as a probability histogram like this. It gives us an idea of the shape of how the probabilities are distributed. And then we could express a probability distribution with a formula. Some of our continuous probability distributions we'll express with formulas. We'll look at some of our discrete ones even later in this unit. We will see some formulas for those distributions. This could be expressed using this formula, could give us the numbers 0.25, 0.50, and 0.125 using this formula here of 1 over 2 times 2 minus x factorial times x factorial. So an example we want to look at here is software piracy. Given the country, what is the proportion of licenses that are pirated in those countries? That are basically unlicensed software packages. Is this a probability distribution? Well, first of all, it's not numerical. These are categorical responses here. This country is a categorical variable. So no, this is not. Second, if I add those up, they add to 2.09. What does that mean? Well, these add up to 2.09. Remember, we said they needed to add up to 1. And, of course, all of the probabilities are between 0 and 1. All these are between 0 and 1, but they're not really probabilities. They're proportions of the time. They're relative frequencies. And they're not even that, really. They don't all add up to 1. So this is definitely not a probability distribution because those requirements are not met. So we want to talk about now our parameters of a probability distribution. Remember that with a probability distribution, we have a description of a population. We're not talking about a sample. We are trying to describe the whole population. So what we are looking at in our probability distribution, those are population parameters. They're not statistics. So our mean, standard deviation, and variance are calculated using the population formulas, not the sample formulas. Our formulas then for those, the mean is the sum of all the values of x times their probability. The variance, well, we take each of those values and subtract the mean, square it, and multiply by the probability and add them up. And the standard deviation, we got to do the square root of that. Then we have the second, the alternative formula for the variance, which is, if we're using Excel, it's much easier to do this formula just because it allows us to use sums rather than other things. These formulas are kind of tricky to understand just by looking at them. So let's go ahead and take a look here at an example. So first of all, this is a probability distribution, as I mentioned before, given students that were surveyed number of hours they do during homework a night, and then the probability that they spend that many hours. First of all, is this a legitimate probability distribution? Well, first, these are all numerical, so yes, that applies. If I add these up, do I get a total of 1? Well, if I add them all up, it does add up to 1. And each of those probabilities is between 0 and 1. So yes, this is a legitimate probability distribution. To find the mean, the first step was to do x times p of x. So take the value, this number of hours of homework here, that is our value x, times our p of x. So equals this x times p of x. Of course, with 0, it's going to end up being 0. Do that for each of those, and then we'll do our total. This total right here is the mean, sometimes referred to as the expected value. So what this is saying is the average number of hours of homework, the mean number of hours of homework completed by students is 2.5 hours a night. To find the standard deviation then, actually let's work on the variance first, then we'll do the square root to get the standard deviation. To find the variance, we then take each value minus the mean. So this equals x minus my mean of 2.5. Now, if I were to just leave it like this, Excel would try to keep scrolling down. So I'm going to put a dollar sign in here to tell Excel to stay at that 2.5. I'll do that for each of them. So we get those differences. Next, I need to square it. So x minus the mean squared. All I'm doing is taking this value here and squaring it. So negative 2.5 squared will be a positive 6.25. And I do that for each of them. And then I do that squared value now times p of x. Now that has not been a part of this calculation yet for the variance. So I take the squared times my p of x back here, and I get that. And we'll do that for each of those values. Now we will find the sum of that. So that sum is 1.29. Now this is where we would divide by a frequency, but remember this is a probability distribution, so it adds up to 1. The total frequency is 1. So 1.29 is the variance. The standard deviation then is simply the square root of the variance. So it's going to equal the square root of the 1.29, giving us 1.136 approximately, somewhere in there. So that is the process for finding the mean, the variance, and the standard deviation of a probability distribution. We went through that pretty fast here, so in the video, if you need to go back and pause and whatever to get those steps down, please feel free to do that. Now, before I move on here, I want to find some probabilities here. If a student is randomly selected, find the probability that they study question 1, exactly 3 hours a night. Well, exactly 3 hours a night, that's just right here. 3 hours a night, that's a probability of 0.38. So when we say exactly, we're just looking for one of the values out of that table. What probability of one number? What if I say that they study no more than 3 hours a night? So what this is really asking for is the probability that they study 3 or less. So that x is less than or equal to 3. So this is adding up 0, 1, 2, or 3 hours of homework. So we add up all of those probabilities. We add up these three probabilities here, 0.7, 0.12, so 0.07 plus 0.12 plus 0.24 plus 0.38, and those will add up to 0.81 probability. Now, to be honest, what I did there is I used a complement. The complement of being less than or equal to 3 would be the probability of being greater than 3, which is only the 4, the 0.19. So I used 1 minus the 0.19, which gave me the 0.81. So rather than adding up those four numbers, I just took the other number, the 0.19, and subtracted it from 1 to get what was left over. But what I really want to point out now is the difference between what we just did there, probability of no more than 3 hours a night, and the probability of less than 3 hours a night. So this is slightly different. This is the probability that x is strictly less than 3. And the difference here is this does not include the 3. So this is just probability of 0 plus probability of 1 plus probability of 2 without the 3 included. So it's just going to be 0.07 plus 0.12 plus 0.24, which is going to give us 0.43. Quite a different probability. The difference is the 3 is not included. That 0.38 probability isn't in there. So being no more than 3 is a significantly different question than saying less than 3. And so you need to be able to keep that wording straight. Similar to that would be the probability of at least 2 hours a night. So this is probability that x is greater than or equal to 2, because 2 is at least 2. So that would be the probability of 2 plus the probability of 3 plus the probability of 4. So that's the 0.24 plus the 0.38 plus the 0.19, which is going to add up to a total of 0.81. Different than that would be the probability of more than 2 hours a night. So this is strictly greater than 2. So it doesn't include the 2. So this would just be the probability of 3 plus the probability of 4 without the 2 in there, which is just going to be 0.38 plus 0.19, which is going to give us 0.57 probability. So again, similar to what we had over here with the difference between no more than and less than, at least and no more than or more than also give us different things. It's that boundary value. Here, at least 2 included the boundary value of 2. No more than or more than 2 did not include the boundary value of 2. It was strictly greater than 2. So we need to be able to keep those probabilities straight and be careful with the wording when we're doing those probabilities. This is going to be huge when we go over and start looking at binomial probabilities in a little bit. So the standard deviation, as I mentioned, is just the variance and then take its square root. Whichever variance, this one uses the second variance formula, but whichever formula for the variance that you want to put under the square root will work just fine for the standard deviation. So the expected value. So the expected value is the mean of a probability distribution. And what it is on average, we hate using that word on average, but if we repeated the experiment over and over again and found the mean of the results, that would be the mean result. So if we surveyed students over and over again here, so as we surveyed several students, the mean number of hours studied by those students we surveyed should be 2.5 or really close to it, depending on the size of our sample. The bigger the sample, the closer we would get to that 2.5. So find the mean, variance, and standard deviation for the number of births. Well, this one's a pretty small distribution, so it'll be pretty quick. So the mean, we do x times p of x. So 0 times 0.25 gives us 0. 1 times 0.5 gives us 0.5. 2 times 0.25 is 0.5. That adds up to 1. Makes sense that the average number of females out of 2 births would be 1. You'd expect about half of them to be male, half of them to be female. The variance then, we go through the formula. This is using the alternative formula. We have a variance of 0.5. For this class, you're always going to be allowed to use Excel for those calculations. So I recommend, again, you look over this worksheet here that we did and get good at using that to find variance and standard deviation so that you don't have to use these formulas. So the standard deviation is the square root of the 0.5, giving us 0.707, or 0.7 is the standard deviation. So what that's saying is out of 2 births, we expect 1 female with a variance of about 0.5, or standard deviation of 0.7 females. So let's talk about significantly high values or significantly low values for our random variable. So the rule of thumb states that if we have 2 standard deviations, if we go that far below the mean, we expect most of the values to be larger than that. Or if we go 2 standard deviations above the mean, we expect most of the values to be smaller than that. In other words, most of our values, it ends up being about 95%, should be within 2 standard deviations of the mean. So if we have a value that's more than 2 standard deviations less than the mean, that's a significantly small value. Or a value that's more than 2 standard deviations larger than the mean, that's a significantly high value. Well, let's apply that to our example here of the female births. The mean was 1, the standard deviation of 0.7. 2 times 0.7 is 1.4. So the mean minus 2 standard deviations would be 1 minus 1.4. That's a negative 0.4 female births. Can't have a negative number of females out of 2 births. The high end would be the mean plus 2 standard deviations. Well, that would be a mean of 1 plus the 2 standard deviations of 1.4 would be 2.4. Again, we can't have 2.4 females out of 2 births. So it's not possible to have any significantly high or significantly low values for this particular experiment. So that gives you the limits of negative 0.4 and positive 2.4. We can't have anything above that, so there's nothing that is significantly large or small. So based on these results, we conclude that 2 females is not a significantly high number. It's not unusual. If it happens, it's not a statistically significant result. Generally, what does it mean to be statistically significant? Well, if whatever happens, so basically we make an assumption and we build our probability distribution around that assumption. And then if we actually have a result that occurs that would have a probability of less than 0.05 based on that assumption, then we would say that that is either a significantly high result. So if it's so large that there's less than a 0.05 chance of getting a value larger than that, that would be a significantly high result. If it's so small that the probability of getting a value smaller than that is less than 0.05, that's a significantly small result. Now, both of these slides indicated that 0.05 is not an absolute rigid value. It's adjusted by the situation. The 0.05 is the most commonly used value, but what the 0.05 represents is that is the chances that we could get that bad sample even though our assumption was true. So basically it ends up being, that's the chance of rejecting our assumption even though it might actually be correct. So if there's a situation where it's absolutely vital that we don't reject that assumption unless it's wrong, then we might use smaller values for an unusual probability. So the rare event rule, like we said, is if we make these assumptions, and then we observe an event that has a very, very small probability, if that assumption were to be true, well, then we decide that the assumption has to be incorrect, that we assume that an extremely rare event doesn't occur. So expected value is a very important value as far as analyzing the fairness of a situation. Vegas uses this for setting odds for their different games and stuff like that, setting the payouts. The expected value is just the mean of the distribution, but it's weighted taking into account gains or losses based on some sort of situation around those probabilities. So for example, let's say we're looking at betting $5 in Las Vegas at a casino. Do we want to bet 7 on a roulette wheel? Or do we want to bet the pass line in a game of craps? So in roulette, there are 38 possible numbers. Betting a 7, well, that's only 1 out of the 38 possible numbers. If you win, you get $180. Well, remember, we paid $5. So if you lose, you've lost $5. If you win, you've gained $175. The chances of gaining the $175 is only 1 out of 38. There's only 1 7 out of 38 numbers on the wheel. So the other 37 out of 38 chances, you're going to lose your $5. So we have lose $5. That's a 37 out of 38 chance. Or gain $175. That's a 1 out of 38 chance. We find those numbers and add them together will give us the expected value here. In craps, the pass line, so the chances of losing if you bet pass are slightly better than half, 251 out of 495. So that'd be losing $5. So the chances of losing $5 times that probability of 251 over 495. If you win, you gain $5, and that probability is the other 244 out of 200 or 495 chances. Again, you multiply those out and add them together would give us our expected value there. So let's see. Now these are Vegas odds, so we're expecting both expected values to be negative because Vegas is going to win. And negative means it's in favor of the house. So for the roulette wheel, -5 times 37 over 38 gives us a negative 4.868421. The positive 175 times 1 out of 38 gives us 4.605263. We add those up, we get a negative 26 cents. So that means every time you play, every time you bet 7, on average, the mean will be that you'll lose 26 cents for every time you play. You might win in the short run, but in the long run, you're going to lose 26 cents every time you play, which means every time somebody bets 7, the house is going to profit an average of 26 cents. That's how casinos make their money. In the craps table, so the -5 loss times the 251 out of 493 gives us a negative 2.535353, or the $5 win times its probability of 244 over 495 gives us a gain of 2.4646. We add that up as a negative 0.07. So if you bet $5 on the pass line in craps, on average you would lose 7 cents, whereas the betting 7 on the roulette wheel, on average you would lose 26 cents per time. So your better bet is to bet pass in craps. Either way, you're going to lose. Like I said, this is how the casinos make their money. They set these so that it's a negative expected value so that you're going to lose. In the long run, you're going to average out to a loss in those games. So now I want to focus in on a special discrete distribution called the binomial distribution. And I am actually going to come back and do a separate video on this in just a few minutes.